Alright, so last time we began our discussion of classical bits, which are units of information that can either be shown as a 0 or a 1, and the strings that you can create in binary that represent numbers in base 10. Now we're going to start talking about circuits and gates, which is essentially ways that we can visualize and manipulate these bits. So let's just say we have a binary string represented by 0, 0, 0. We want to pass it through a circuit and have it end up as a 0, 1, 1. I want to note, from like a notation standpoint, that when you read a circuit, you read it from left to right. When you read a binary string, you read it top down. And of course, when you are translating that binary string into a base 10 number, you start from the right and go to the left with increasing powers of 2. So what can we do to make this transformation happen? Well, we do that through what are known as gates. So there's two types of gates that we can see in classical circuits, and those are single-bit gates and multiple-bit gates. So for the classic single-bit gate, we have the NOT gate, which is represented as such. Now, if the name wasn't obvious, the function of a NOT gate is to turn a 0 into a 1 and a 1 into a 0. So you're essentially saying, whatever I put in, not that. So what's not 0? 1. What's not 1? 0. Very straightforward. So what we could do then, with this question mark in the middle here, is for the top bit, nothing. For the middle bit, add a NOT gate, so we can turn that 0 into a 1. And for this one, we can turn that 0 into a 1 as well. But that's not the only way that we can do that. Now we can start talking about the CNOT or controlled NOT operation, which is a multiple bit operation. Essentially, the function of a CNOT is to have a control bit and a target bit represented respectively by C and T. And if C is equal to 1, then you just simply NOT T. So as an example, we're just going to look at these 4 cases of 2 bits. So here the control is 0, here the target is 0, so this is not a 1, so it doesn't change, so you end up with 0, 0. Simple enough. Same case here. The control bit is not 1, so there's no NOT being performed, so this, of course, returns 0, 1 as well. This is where it changes. The control bit is, in fact, 1, which means this would change from 1, 1, since you're performing a NOT on this 0 here. And with this, since the control is a 1, you NOT this, yielding 1, 0 in the end. Hopefully that's straightforward. Another way that we can sort of mathematically represent this is we go from C to C and T to T modulo addition to C. So as we discussed in the last video, modulo addition 2 essentially means if you have an even number, you get a 0. And if you have an odd number, you get a 1. So in this example, we can see that this T plus C is 0 plus 1, which is 1. And then 1 plus 1 is 2 in modulo addition that yields a 0, which is why we get that there. So to sort of round out our discussion of CNOTs, we can take a look at the circuit again. Well, we want to change this into a 1 and this into a 1. So, of course, if we want to use CNOT at all, we need to have at least 1, 1 coming in from the left. So let's just NOT this 1. All right, simple. And then this, we'll say, this is the control, this is the target. So this is going to turn into a 1 when it goes through the NOT. It's going to control the operation here, meaning it's going to turn this from a 0 to a 1, and of course we will get a 0, 1, 1 at the end. There's a final multiple qubit gate called the Tafoli, T-F-F-O-L-I, which is functionally the same as a CNOT, except it has 3 qubits instead. So you have a 1, 1, 0 here. Both of these being 1s turns this into a 1 as well. If this were 0 or this were 0 or they were both 0, then we would not have this transformation happen at all. They both have to be 1. So hopefully that gives a pretty introductory explanation of some of the classical circuits and gates that you might end up seeing.